Let's take an example like this one. What if we want to do this function, okay, g of x? Now, what's the parent function and why? The parent function. So the parent function is just, you know, what does that mean? It means what's the most basic function that this is built around. So is it when we say a parent function, it's always going to be just a handful of different possibilities. It's not like it could change very much. It's either going to be a quadratic, in which case it'll be at y equals x squared, f of x equals x squared. Or it's going to be an absolute value. You know, f of x equals the absolute value of x is the starting place, and then we do some other stuff to soup it up. But what's this one? What kind of function is this? I'm looking at this one right here. What kind of function is that? Okay, what kind of radical? I mean, what is that? Square root, that's it, it's a square root function, right? Did everybody see that's what I mean by the parent function? So if you eliminate all the numbers in there, because the numbers are extras, right? If we just get rid of all the numbers and just look at just what's being done to x there, well, it's a square root function, right? Does everybody get that? That that's what we mean by the parent function? So we want to do this to the parent function, the square root of x. Okay, so the first thing we probably want to do is let's go back and remind ourselves what that parent function looks like, right? So if this is a square root graph, this is one that we want to, really we don't have very many we're working with right now. This is the second. We'll move on. We haven't really talked in detail about parabolas yet. That's coming up real soon. We've really only done the V-shaped absolute value graphs we've talked about quite a bit. And then this is number 2. And square root graphs always look like this. They have a starting point, and then they start steep, and they level off. Okay? That's what the parent graph looks like. Now, we can do stuff to that. We can reflect it and stretch it and translate it, do all that kind of stuff. But this is where we're starting with an square root parent function. So let's look at what these points are. If we start at the vertex, here's how we want to think about this. When we move 1 away from the vertex, that's like inputting a 1 into this square root graph. What's the output? 1, because we're just taking a square root, aren't we? Square root of 1 is 1. The input is always going to be, when we think about the input, it's always going to be the distance from the vertex, right? That's the starting point. So the horizontal distance is 1. We input a 1, we get back a 1. If I input a 2, it's not very convenient. If I input a 2 in this, I get back to square root of 2. Well, the square root of 2 is like 1.4142, blah, blah, blah. So that's not convenient. It's not an integer. So we don't really put a point there. Obviously, there is a point there, but it's not a convenient one. Same thing with 3. Square root of 3 is, that's not convenient either. Square root of 4 is, right? If I input a 4, I'm outputting a 2, right? If I input a 5, that's not convenient, not convenient. 9 is, though. The square root of 9 is 3. If we kept going out there, square root of 16 would be 4. So you can kind of see what's happening here. This curve is flattening out. As we go further and further and further out there, eventually we get really big x values and not very big y values, right? So remember, the x values are always going to be, as long as you're bigger than 1, the input values are always bigger than the output values, right? So there's our parent graph. So what's this going to do? This is, we're comparing this to, if we're going to do horizontal stuff. So we're going to horizontally dilate, okay, and then we can translate too. But we're not going to worry about the vertical part, so we'll forget about this part. If f of x is just the square root of x, we can write all of our transform graphs in this way. Those 4 parameters tell us everything we need to know about any possible square root graph we can draw, right? What do h and k do? Good horizontally and vertically. And being as the starting point, or special point, for the parent graph is at the origin, if I scoot it horizontally by h, well, that's just going to be the x-coordinate of where that vertex ends up, right? Being as it starts at 0, 0, if I translate it vertically by k, then wherever it ends up, that's going to be the y-coordinate of the vertex. So we can just think about h and k as being the coordinates of our special point, right? What's a? What is it? No, actually, just in general, what is it? It's 1 here, but what is it in general? You're right, it is 1. What is it in general? What's it mean? It's the number being multiplied by the output, right? By the whole function. So what does a do? Dilates it which way? No, vertically. Remember that when we multiply the output, the whole thing, you know, this is whatever y value the square root is calculating, we're going to multiply that by a. So it's stretching and compressing vertically, right? And if a is negative, it's going to reflect it vertically.
I don't know, it's pretty cold outside, so.
It is, I know. So a dilates and reflects vertically. How about B? That's the horizontal one, right? B dilates and or reflects horizontally. So in this case, what are h and k for g of x here? Yeah, so what are they? 0. Yeah, they're 0, because if I plug in 0 for h, well then h minus 0, or x minus 0 is just x, right? So that just becomes a plain old x. And then adding a 0 at the end, well, we wouldn't write that, right? It just isn't there, so it's 0. What's a? 1, because it doesn't show up out front. It's a coefficient, it's a multiplier. If a multiplier doesn't show up, it equals 1, right? What's b? 2/3. Okay, so now we're getting somewhere. So we know that the value of b, we can see from the function, is 2/3, right? Now we got to think about the second part of this. That's b. What is the horizontal dilation factor? So this is the one this horizontal stuff is kind of a brain twister a little bit. It's confusing at first. And after a while, you get the hang of it. But remember what we talked about late last week. Okay, we talked about how if you took like a rubber sheet and we graphed a function on it, and if I stretched it vertically, what was the effect horizontally? Shrinks, right? If we stretch it vertically, it's going to compress horizontally. What if we take the same sheet and we stretch it horizontally? It's going to shrink vertically, right? So we said that they have inverse or opposite behaviors, right? So then, what do you think we're going to multiply by here? If this 2/3 were out front, it would be, what would be happening vertically to this function? It would be shrinking, wouldn't it? It's less than 1. Everybody agree? This would be a vertical compression. So if it's inside, what do you think that 2/3 must be doing? Not vertical. It's got to be stretching horizontally, right? Because a vertical compression always goes along with a horizontal stretch, right? So this 2/3, a value of b equaling 2/3, has to equal a horizontal stretch. But multiplying by 2/3 is going to make something smaller. So what do we have to do to that value of b so that when we multiply by it, it's going to make something bigger? Go ahead. What was that, Shannon? Flip it, right? Take the reciprocal. So the horizontal dilation factor, let's call that d, or dilation factor, is 3/2. It's going to be the reciprocal. That's what we multiply by. It's always the reciprocal of b, okay? So now what? If we're going to multiply by 3/2, then let's start off with this point. Each of these points on the parent graph, we always start by comparing to the parent graph. This is our starting point, and then we're going to tweak it by dilating it horizontally. So if we're going to take the for a vertical difference of 1, the horizontal distance from the vertex, and that's what we're dilating, right, is the distance of each of these points horizontally from the vertex. So if this distance is 1, we're just going to multiply that by 3/2 and get an answer of 3/2. So the horizontal distance is going to change from 1 to 1.5. Okay? So that point gets pushed to the right, which makes sense. The vertex is going to stay put though, right? So all these points are just going to get stretched away from the vertex, or the initial point, I guess we should call it. Okay, what about the next one? Next one, we know that normally on a parent graph, for a vertical distance of 2 from the vertex, we would expect a horizontal distance of 4, right? So we've got to multiply that by our dilation factor of 3/2. I want you to notice something that happens here that's convenient. So 3/2 times 4, make the 4 into a 4/1, and notice that the 2 on the bottom cancels, right? 4/2 reduces to 2/1, and so we just get 6 for our answer. Okay, why did that happen? Why did the 2 on the bottom cancel in this case? 4 was a convenient number to use. How come? Because I could, and what told us that we could? Okay, 4 is a multiple of 2, right? And why is 2 important? Because that's the denominator of what we're multiplying by, the dilation factor. So that gives us kind of a general rule, doesn't it? When we're trying to pick convenient convenient points to dilate, we always want to look for distances from the, from the starting point, or the special point, that are multiples of whatever the denominator is for the dilation factor, right? Okay. So then, so this gets pushed over from 4 over to 6, and now we got 2 points. It's easy for us to just make a sketch of the graph, or recognize the graph, right? We don't even really need this one. All we need is the vertex and another point that we can accurately target on the graph, and we know what the basic shape of a square root graph is going to be. This is just going to be a stretched version. We know that it starts steep and it gradually levels off, right? All we really need are 2 points to get a basic sketch. And think what you're going to be doing on Moodle. On Moodle, you're going to be choosing from a whole bunch of different options, right? So you're just going to pick the option that has a vertex there and goes through that point, right? And that's going to be the right answer. Make sense? Okay? So what's different about this one then? What's the value of A here? One. So nothing's happening vertically, right? What's the value of B? What is it? Not 9. Negative 9. Right? B is negative 9. And then what about H and K? Okay, but what are their values? What's H? 1. Good. It's 1 because it's the value that's being subtracted from X. And what's K? What's K? 2. Yeah. Okay, so then this problem looks a lot harder because there's more stuff in there, but it's not. It's the same problem, only we're just starting, instead of starting from the origin, we're starting from the point 1, 2 with our parent graph that we're going to dilate, right? That's it. It's the only difference. Okay, so then if B is negative 9, what are we going to multiply by? What's our dilation factor? What's that going to be? Not 1/9. Derek, what's it going to be? Yeah, negative 1/9. Good. There you go. Hear your voice there, Derek. That's pretty good. Ventriloquist. So multiply by negative 1/9, and then this is essentially what we do, right? We're just going to move. Here's the point 1, 2. That's where our starting point goes. Here's our normal parent graph, and we're going to multiply the horizontal distances from the starting point, the initial point, by negative 1/9. So what's gonna be a convenient one to use? We wanna use one that's a multiple of 9, right? So over 1 isn't gonna help us much. Over 4 is gonna give us a fraction, but over 9 and up 3 from the initial point works great, right? So instead of having a vertical distance of 3 and a horizontal distance of 9, we're gonna multiply that 9 by -1/9 and instead get -1. So the point that is up 3 from the initial point is gonna go from there over to there. So it's getting squeezed and reflected, isn't it? Right? So we end up then with, that being that's our graph. All we need is 2 points, one there and one there. And we know it starts steep and levels off, but this time it's going in the other direction, so.
Wait, how do you get the 3?
Say it again?
How do you get the 3?
Because for our parent graph, let me go back here with that. Let me go back to this guy, right? We know that for our parent graph, we go over 1 and up 1, we go over 4 and up 2, or we go over 9 and up 3, right? From where? Not from the origin, from the starting point that's at HK. In this case, H and K are just 0, 0 and 0, right? But in the second example, H is 1 and K is 2. So we move from there up to there, but otherwise it's the same, right? From there, if we go up 3, we would normally go over 9, right? Because that's just where our parent graph is starting at. So we're going to multiply this horizontal distance by the dilation factor and get -1. So instead, we're going to go up 3 and back 1. Okay? So there's our graph. Last one. How about this? This time we want to write a function of this form. So we're not writing it in terms of A, we're writing it for B. Okay? What do we know here about H and K? What are they? They're easy.
-1.
Yeah, just the coordinates of this point right there, isn't it? That's not too hard. So H is -4, K is 1. What are we multiplying by here? That's the question, right? So describe the location of this point right here relative to the starting point.
3 over 1.
And so we know we're vertically, the distance is 3 from the starting point. It's up 3 and over 1. So if we're talking about B is a horizontal dilation, right? So this point has to have been moved horizontally from somewhere, right? Everybody agree? Because where B is horizontal stretches and compressions. So we have to ask ourselves, where would the starting point have been for the parent function? If I'm going up by 3 from the initial point, the starting point, how far would I have to move to the right on the parent graph, square root function? How many? 9, right? Normally, I would go up 1 and over 1. I'd be going, for a rise of 2, I've got a horizontal distance of 4. For a vertical distance of 3, I've got a horizontal distance of 9, right? See what I'm saying? So this point has been moved from there back to there by our dilation factor of what you're trying to find, right? What's going to do that? Okay, this is an unrelated question. It's going to seem like this is really weird, but I want you to think about, so there's where we start, there's where we end, right? Start with 9, end up with 1. Agree? This is going to seem weird. Let's talk about this question for a second, because this is the same concept. But this will make it easy for you to make this jump. If you start with 180 bucks in your bank account, you end up with 150. By what factor? Whenever we talk about a factor, factors are things in math that we do what with? Multiply. Yeah, factor means we're multiplying by it, right? By what factor did your balance change? Right? Meaning, what do I have to multiply by to start with 180 and get 150? Right? This is the same idea as a dilation factor. We're starting with a parent amount, and we're ending up with, and they call it a child amount, we're ending up with some amount that's been transformed. And we want to know, what do we do? How do we get from here, whoops, how do we get from here to there? Well, what do you think you do? What would I multiply by? What am I going to multiply 180 by to get 150? That fraction, right? Whatever your final value is divided by your initial value, right? So that's the change factor, or for us, it's a dilation factor when you're talking about functions, right? So what's that going to be then? That's just going to be 150 over 180. Well, look what happens if I multiply that by 180, duh, what's going to happen? The 180s cancel, and I get 150. Makes sense, doesn't it? Right? So then we'd want to simplify this. So 150 over 180, I could divide by 10 and get rid of the zeros. And then what? 15 over 18 is what? 15 over 18. What can I divide both by? So 5 and 18 divided by 3 is 6. There we go. So 5, 6 would be the answer, right? So then what about for us? Well, what's our starting value? Our starting horizontal distance. What's that going to be? John, what's our starting horizontal distance here? We're starting with a parent function, and we're ending up with, we're compressing it to get this thing.
It's not negative 4, is it?
No. No, we're saying that here's the value. We know that this is what we end up with, right? We know that this is what we get. Do I have a picture? Yeah, right here. No, there. I guess we don't have a picture. That's it right there. So we know that normally when we rise by 3, right, because that's where that point is, this is our starting point. Normally, if the distance on the function, the vertical distance is 3 away from the starting point on a square root parent graph, well, we've got to go downstream. We've got to go 9 to make that happen, because the square root of 9 is 3, right? So normally we have to clear over here to go up by 3, right? So normally, the parent distance would be 9, right? But we've changed that. We've squeezed that down to there, right? The final distance for our function is only 1. So what do we say then? How do we find a dilation factor? It's always final divided by starting value, right? So what are we going to get? What's that going to work out to be? Taryn, what's that going to be?
So is that going with like the last fraction we had, or?
Well, I mean, kind of, yeah. It's the same concept exactly as this. In this case, instead of a final balance, account balance, it's just going to be, all we're talking about when we're talking about a horizontal dilation is we're starting with a point that is some horizontal distance away from our special point, right? Whatever that is. In our case, it was 9. And we're going to compress all the points, so now that one ends up being, instead of the function doing this, it's going to do that. It's going to get steeper, right? Instead of being 9 to the right, it's only 1 to the right. So what do we do to move from a horizontal distance of 9 to a horizontal distance of 1? We divide 1 by 9, don't we? Right? See what I'm saying? We're just going to divide that value by that value, right? How far do we end up being to the right compared to our parent graph? Because we're always starting with the parent graph and tweaking it to get this one. See what I'm saying? No? We'll do another one. We need another one. Okay. So then our answer would be, based on this, you told me h and k are, did you tell me h and k on this one? I can't remember. I think you did. -4 and what's k? 1. Yeah, you did. That's right. And then to make this thing compress like this, we're going to have to multiply by 1/9, which makes sense. I mean, we've got to make it a lot smaller. We've got to make this distance, normally it would be a horizontal distance of 9. I've got to squeeze it down to 1. I've got to make it 1/9 as big as it was before. Right? Here, try another one. This, I know this is tricky. Okay, let me pull up, oops, on here. Okay. Everybody try this one. Oops. Oh, this one. So get out your notebooks and that one. That's what I wanted. Whoops. Try that. So you got to pick out from that graph, you got to pick out the values of h and k and b, right?
What? Oh, yeah. Can you zoom in a little bit more?
I can't see that.
Yeah, I can. Michael, you have your phone out, do you? Okay, if you did, you'd want to put that away. That'd be. Okay, how's that? So what is the x-coordinate of the starting point, Aiden? Okay, so that's h, right? Maritza, what's k? Say it again. No, okay, wrong point. Right? We want to use this isn't the point we're interested in. That's our special point, right? That's the one that normally would start off at the origin.
Is it 5?
It's 5. Yeah, it's 5. So h is -2, k is 5, right? So we know those two things. We can put that stuff in right now. Let's just start with a template here. We know that our answer is going to be in the form the square root of b times the quantity x minus h plus k, and you already told, whoops, didn't get out of the radical, plus k, and you already told me that k is 5 and h is -2. So what's x minus -2? Plus 2, okay. So all we got to do is find b, right? So what's going on? This is our starting point, right? We're ending up. What's a convenience? So we're given another point here that we're just going to use, okay? What's the horizontal distance from our starting point to that point?
9.
Not 9, it's,
1?
no, you're on the right track, but I'm starting here. In which direction am I going?
Negative.
-9, right? So we end up with our final horizontal distance is -9. What's our vertical distance from this point to this one? 1. Okay, so if the vertical distance is 1, that means that this point must have been pushed there from where? Where would it have started off with our parent graph? Over 1 and up 1, exactly. Because if I'm going up 1, normally I would go over 1 and up 1 to get to that point on my graph, right? So I'm starting with, so that's my starting value, right? That's the starting. And I'm just going to call it delta x, meaning just the the horizontal distance. We can call it whatever we want to, that's just a shortcut. Delta x equals positive 1. Right? How much did the x change from there to there? What about our final one? How much does it change? Not 9. Negative 9. So to go from here over to here, this distance is negative 9. So what do I multiply by to go from 1 to negative 9? Well, it's always just final divided by initial, right? So D just equals negative 9 divided by 1, which is negative 9, right? Okay, so that's what I'm going to substitute for, well, actually it's not. That's my dilation factor. So what's B?
Multiply it by 9.
Remember,
Isn't it one? Isn't it gonna be negative 1/9?
negative 1/9. It's the reciprocal for B, right? Whoops. Oh my gosh. So let's do this. I gotta go like that. There we go. Everybody like that? Let's check it. See how we did.
So would you always flip it for the reciprocal?
For B's.
I'm-
Yeah, for
wait,
B's.
I'm-
For A's, you don't. A's, the dilation, what you multiply by is the dilation factor. But for B, they're that reciprocal behavior. Horizontal stretch is, right? Remember, we have that opposite thing going on. Okay, let's try one more. I want to make sure we got this down. Let's do one where we just pick. Okay, let's do one like this. Okay, so where is this graph going to be? Where is the starting point going to be for this one?
You see it down.
Negative. Or no, 1 negative.
Well, I want you just to look at this for a second. So, Gio, what's going to be, let's start off with our vertex, or with the starting point. What are the coordinates H and K going to be? 5, 1. Okay, everybody see that? So we know that it's going to be H is 5, K is 1, right? So we could summarize everything. Let's just put a summary over here, and then we'll go find the graph. So H and K equals 5, 1. Okay, what about this guy right there? What's that telling us? What's B?
It's
It
gonna
goes over
go
right
over 9 up.
Okay, hold on now. B is what? 9. But if B is 9, more importantly, what's our dilation factor?
1/9.
I'll call it DF so we don't confuse it. Dilation factor equals 1/9. So that's what we're multiplying by, right? Okay, so what's going to be a convenient point to use then if we're multiplying by 1/9? We want to multiply by a delta x, by a horizontal distance of probably 9, right? Because that's convenient. So how far up vertically would we have to go normally to go over 9, to have a horizontal distance of 9? 3. Good. So this is telling us, very good. So this is telling us right here that we're going to go up 3, and we're going to go to the right 1/9 times 9, which is how far?
Okay, I got it now.
See what I'm saying? So we're going to go to the right only 1.
Why are they all 1?
See it again? Because I didn't want to make them horrible fractions. So they could be, you're going to get answers that are going to be like,
I got it.
they're going to be, you might have a 9 in there, you might have a 4, you might have a 16. See what I'm saying? So they end up being
Just
convenient.
all the way below the square root.
Well, we've just, yeah, that's just been kind of weird chance, but they won't all be 9s, I promise. Okay, so let's go find this one then. Let's go find this one. So you guys tell me, as a group, tell me when we get to this one.
Okay. Wait, what?
Whoa.
Was it that one?
It's that one, isn't it?
Yeah.
Right? Because the vertex is at 5, 1,
And then it goes
And-
3 over 1.
up 3 over 1. Instead of going up 3 over 9, we go up 3 over 1.
That's confusing, but okay.
I mean, I think you just got to practice it now, which I'm going to let you do.
I got, okay.
Okay?
Yeah.
So I'm going to turn you loose. Get this.